Serious problem. I realized that all of my recordings had audio issues and none of my audio got picked up. So I'm doing a little voiceover. Um, so it's very frustrating. But you know what? It's better than nothing. So let's talk about inverse functions. I believe in my intro, I started out by talking about how messy my studio is, and it's definitely time for me to do some deep cleaning. But talking about inverse function is much more of an urgent matter. So here it goes. Let's imagine we have a linear function, y equals 2x plus 1. This is a simple linear function, and here I am going ahead substituting different values. I just created a very simple table, and I found values of y according to the different values of x, as you can see. So when x is -2, y is -3, x is -1, y is -1, 0, 1, 1, 3, 2, and 5. And here I'm going to go ahead plot these points. I plotted the coordinate points and I graphed the linear function. And from here on, I'm going to take a look at its inverse. So what I mean by that is I'm simply going to switch the x and y. So all of my x values would now become my y values, as you can see, and all of my x values would now become my y values. So my domain becomes range, range becomes domain. And I'm going to go ahead and not substitute. I'm going to go ahead plot these coordinate points, as you can see in purple. It's more fuchsia, I think. I went ahead, graphed the inverse function, and now I am drawing y equals x, and that's because, as you can see, y equals x serves as my line of reflection. So the original function, the given function, y equals 2x plus 1, is actually reflected over y equals x to give the inverse function. And now that I have the graph of the inverse function, I can actually try to find the inverse function equation by finding its slope, which is half. And I'm going to put that in my standard. It's not a standard form, but I'm calling it standard because we've seen it a lot. Our good old trusty slope-intercept form, and I've substituted -1 and -1 accordingly, and my y-intercept turns out to be -half. So my inverse function is y equals half x minus half, as you can see. And actually, if I just go ahead, switch x and y in my given function, so I get x equals 2y plus 1, and I try to solve for y in terms of x, so I go ahead, get x minus 1 equals 2y, which would ultimately give us half x minus half equals y, and voila, that turns out to be exactly the function equation that I get from our graph. So there you go, we found the inverse. Let's go ahead, take another example of y equals -4x plus 6. So again, we switch x and y, so I get x equals -4y plus 6, and which then turns out to be x minus 6 equals -4y, and it eventually gives us -1/4x plus 3 over 2 equals y. So that's my inverse of the given
If I
function.
go ahead, rearrange my terms so that I can define y
And
in terms
now
of
let's
x,
try
what
to
I'm going to
actually
get is
graph
y
it
equals half x
so that we
minus
can
half, which is
verify
exactly what we
the
got
relationship
from
between these
looking
two
at
functions once
the
again.
graph of the
And as you
inverse
can see, I
function.
have a hard time drawing a
So
straight line,
that's how you go
relatively
ahead,
straight line.
find the inverse function of whatever the given function. You can simply go ahead, switch.
So so there goes my given function, y equals negative 4x plus 6. And remember, we have to make sure that its inverse function is a reflection of the given function about y equals x. So there is my inverse function, and I went ahead, just graphed it from the equation that we found. And as you can see, I am drawing y equals x to demonstrate that these two functions are indeed inverse of each other. I have a very simple example over here to demonstrate how to verify if functions are inverse of one another algebraically this time. So let's imagine we have a linear function f, which is y equals 2x essentially, and its inverse would be half x, and that is the function g of x. And we're going to use composite functions. We covered composite function in last lesson. So let's go ahead and find function of f of g of x, and that will give us 2 times half x, which would be x, and g of function of x would also give us x. So now I know that g of x and f of x are inverse of each other because why? The composite functions, function of g of x and g function of f of x, both give us x. So therefore, they're inverse of each other. So now we know how to verify if the functions are inverse graphically, but also algebraically. Let's take a look at another simple example. We have a linear function here, f of x equals x plus 4, and we have g of x, which is x minus 4. We're going to see if they're inverse. So I go ahead, set up the composite function of g of x as such, and then g function of f of x as such. Now, x minus 4 plus 4 gives us 4x, and x plus 4 minus 4 also gives us x. So they are inverse. Very simple, right? Let's take a look at another example. We have x raised to the power of 5, and g of x is 5th root of x. Now, the composite of f of g of x would be 5th root of x raised to the power of 5, so therefore that would give me x, and g of f of x would be x raised to the power of 5, and that is in the 5th root, so therefore it would also give me x. So I know that these two functions are inverse. Number 11, we have a function of x, which is 3 minus x, and g of x, which is 3 minus x. And if I go ahead, create a composite, I would get 3 minus x, so therefore I would get x. And if I were to create another composite function with a g of function f function of x, I would get once again, x. So therefore, these two functions are inverse. So now we know how to verify inverse functions algebraically and graphically. So we are moving on to actually graphing the inverse functions. We have half x squared minus 1. I can go ahead, graph it, easy peasy, not a problem. And I went ahead, drew y equals x, and you can go ahead and reflect it about that line to find the graph of the inverse function. But on top of doing that, what I went ahead and did was I simply found the inverse function again by switching x and y and then solving for y in terms of x. And my inverse function comes out to be square root of 2 times x plus 1. So, and I went ahead, graphed that in blue. Okay, but here's a little question. Taking a look at the inverse function, can this graph pass vertical line testing? Remember, vertical line testing is a way for us to verify if a relation is a function by simply drawing multiple vertical lines through the graph, and we have to make sure that only one point on the graph intersects per vertical line, remember, because in order for us to have a function, we have to make sure that every input comes with a distinctive output. But if I were to go ahead, do vertical line testing right on this inverse function, or inverse function I should say, I get more than one intersection. So therefore, this does not qualify as a function, right? And in order for us to make this step a little bit easier, instead of doing vertical line testing, we can conduct horizontal line testing to see if a function's inverse would be a function indeed. If I were to reflect my inverse graph along with all the vertical lines that we drew, reflect all of them about y equals x, what we would notice is that all the vertical lines would then be reflected to, all the vertical lines would become horizontal lines, yeah? And we call this horizontal line testing. So vertical line testing is for us to verify if it's a function. Horizontal line testing is for us to verify if this function, its inverse, would be a function. It would definitely have an inverse, but we are interested to know if that inverse is indeed a function. And we call this horizontal line testing, and that's simply because the vertical line testing that we would do, we are simply reflecting about y equals x again. So just drawing multiple horizontal lines through the original given function would be enough for us to see if its inverse would be a function or not. As you can see, this function does not pass. The function would pass the vertical line testing, but it would not pass the horizontal line testing because, as you can see, we have multiple intersections. By multiple, I mean more than one per each horizontal line. So therefore, its relation is not a function. Let's go ahead, try another one. Take a look at number 16. we have negative x squared plus 3. And this time they've specified our domain to be bigger than x being bigger than 0. So if I were to go ahead, graph that, graph only this part. So now we know for sure that this is a function. We don't have to question that, but let's go ahead and see if its inverse would be a function by conducting a vertical line testing, a horizontal line testing. As you can see, each horizontal line only has one intersection, so therefore this passed horizontal line testing. Its inverse is a function. And then we can go ahead, graph the function, the inverse function, by simply graphing y equals x and then reflecting about it. So so I believe it would look something like this. This would be the inverse. I should have really drawn with a different color, eh? This would be its inverse. There you go. Let's take a look at the cubic function. This is what I'm going to get. Okay, so this is obviously a function. It passes the vertical line testing. Let's see if it passes the horizontal line testing. So, There you go. It absolutely passes the horizontal line testing. Horizontal line testing. So I'm going to call it HLT for short. And that means its inverse is a function. Oopsie. Go ahead, graph it. So y equals x. So that would be right here. And then right there. This would be my y equals x. So my inverse would look like boom, and then boom. This is what it would look like. Ta-da! And we can find the inverse function as well by simply switching x and y. So I would get x equals 1/4 y cubed, and that means 4x equals y cubed. So cube root of 4x would be the inverse function. There you go. In this lesson, we covered how to find an inverse function algebraically, that is switching x and y and solving for y in terms of x, how to find inverse of a function graphically, that is reflecting the given function's graph about y equals x, and then how to verify if the given functions are inverse of each other using composite functions, and that is also using algebra. And again, how to verify if a function's inverse would be a function by using horizontal line testing. So make sure to remember these big four because these are very, very important.